I am Daniele Rispoli. I work for Submer Immersion Cooling. We produce immersion cooling solutions. So you've probably seen the unit that we have at the entrance. We have a big black tank. That's our smallest form factor of immersion cooling solution. But as many of you in the room, I didn't really start in the HPC area. I mean, the beginning of my career was actually in computational logic. I started writing like Greek letters on blackboards and then trying to write software that proved these theorems. And then I figured out that there wasn't a lot of money to be made in this kind of thing, so I decided to use my much more practical skills, and I joined one of the Formula One teams. I started working for Scuderia Toro Rosso. I was the HPC engineer there, and I took care of all of their CFD simulations and the cluster that they had for the external aerodynamics of the car. And after a couple of years, I decided that I wanted to learn a little bit more about HPC, and by doing that, I decided to do that by joining a company that was called Cluster Vision. The slide is a little bit cut, but yeah, you see. I was deploying a lot of the clusters that many of you probably have used. I've worked with some of you on the technologies that we've had deployed together. I was doing deployments on all type of clusters, so air-cooled clusters, as you can see here, also immersion-cooled clusters, and rear-door-cooled clusters. A lot of stuff. After a while, it was time to move on. Sure, go ahead. In the meantime, I will talk about it. So, in all of these deployments, the things that I have seen was a clear trend towards more density required, especially by the HPC center, and a lot more power being dissipated in small form factor. And that's why I joined Submer, actually, because I think that the way that they approach this problem, especially the problem that we see here, like we have this statement, and we think that by 2023, at least 50% of the HPC installations that will be deployed will be in some way cooled by some form of liquid. And the only way to tackle this kind of problem is to have especially something that can efficiently and reliably take the heat away from these machines that are generating heat. As we all know, computers need cooling because every component that has electricity as an input produces heat as a collateral effect. That's just a collateral effect of computing something useful. And the capacity and the density of this rack is only increasing. We've seen here, for example, that after a certain threshold in which you reach of power being dissipated, heat being generated in hardware, you have to space this hardware apart quite highly. You cannot be as dense if you only use air-cooled, which means you have to build huge facilities, you have to put in there huge air conditioning units in order to be able to keep these machines in an operating environment that they can fruitfully live in. And this problem is only going to get worse because a lot of people, especially in the HPC field, are gearing towards having more and more density per rack. As Miguel said this morning, we are seeing in the HPC space people are wanting to go towards 30, 40, and more kilowatts per rack. But this is not something that you can do in here. And that's why I'm here talking to you about liquid cooling. So there are different types of liquid cooling, and the two types of liquid cooling that I'm going to focus on today are direct-to-chip liquid cooling, which we have already had a little bit of a introduction to this morning, and immersion cooling. I'm not going to talk about rear door extraction cooling. Some people describe it as liquid cooling as well because there's water or some kind of fluid running in the doors, but the fluid should hopefully never get in touch with the hardware itself, so we don't really consider it as type of liquid cooling. Let's start with direct-to-chip liquid cooling. So it's generally, if you're just retrofitting hardware that wasn't designed as the Lenovo machines that we've seen today, that wasn't designed to be cooled with immersion, you have these kits that are coming with flexible pipes, and the thing that they do is that they cool just or mostly the part that they are in contact with. So it basically ignores all of the other stuff like the memory or the other chiplets that are on a motherboard. This means that, of course, it's more efficient than pure air in taking away the heat, and it's been already adopted by several manufacturers, but it's really necessary to keep the fans running and the air conditioning running in this type of scenarios. So you have that on one side, the complications of having liquid very close to your hardware, which is something you're kind of iffy about. And then you also have the costs, which are not being eliminated, of still having air conditioning in your facility. And especially in this type of solution, but also in the ones that are designed only for this, you kind of end up in a situation in which you have a little bit of a lock-in from the vendor. I mean, if you buy one of those very nice machines that we've seen from Lenovo today, they are specifically designed for that type of hardware. They are engineered to have those kind of plates. You cannot just replace the motherboard with something else. You cannot just swap with another model of manufacturer because your infrastructure is going to change as well. And this is also true in other types of situations in which we've seen, for example, in which the producer does also the racks and not just the servers in a way in which the pipes are all integrated in the installation itself. And this also, of course, is not interoperable with other type of hardware. And that's where immersion cooling, according to us, comes in. So in immersion cooling, what we do is we have a big tank like the one that you've seen outside, and the liquid that it's in there is completely dielectric, so it doesn't conduct any electricity. We take the machines, we take out the fans, we take out all of the moving parts. Sometimes we need to replace the thermal paste if it's not compatible with the type of liquid that we're using. But basically, you don't have to do anything else. You just put the machine inside the liquid itself, and it will work. It will work for its lifespan. Actually, the lifespan of this machine is being extended by the fact that they operate inside of this environment, because the environment protects the machine from dust particles. It protects it from moisture. There's no corrosion. It protects it from vibration, and there's a lot less thermal stress because every component in the server is cooled at the same rate. It's a very uniform environment. There are, of course, a few drawbacks to this type of solution, and the most important one that we see is the fact that people are not really used to this type of things. There is a bit of concern in submerging your very much costly hardware, and there is also a bit of unfamiliarity in the fact that this in the form factor, because it's basically a rack tilted on its side. So all of the machines go in from the top. We're going to go there later, and I'll show you. Yeah, there is a little bit of a hurdle to overcome in order to get people familiar with this type of solution, but the advantages we think are worth it. And let me go a little bit over different types of immersion cooling. So there are mainly two types of immersion cooling. There is a type that it's called two-phase liquid immersion cooling, and this is the liquid that we see here at the bottom. It's called two-phase because it has a very low boiling temperature, which means that it boils on contact with the components that are getting hot. It's the boiling that actually dissipates the heat, so that all of these bubbles are taking the heat away very efficiently, because by convection the bubbles just go towards the top, and then they evaporate, and then there is a condensator in the loop which makes the liquid, the evaporation of the liquid again, and it recirculates. The problem with this type of solutions is that these kind of liquids are kind of expensive to manufacture, because they're they have to have a specific boiling point and all of the other characteristics. It's a very complicated solution because it requires all of these condensation materials, so it's not easy to manufacture this kind of solution. And it also can be hazardous, produces hazardous fumes for people to be around with, which means that you have to seal all of these units. They cannot be operated while they're open. You have to seal them, and you have to have special equipment whenever you're handling something like this. And actually, Submer wasn't in the field when we started at the company. We were not. We didn't set out to develop our own fluid. We just wanted to have the cooling solution and the tank itself, basically. And we tested a lot of the liquids that were on the market, but we didn't find anything that was to our liking, that had all of the properties that we wanted, which is why we developed our own single-phase liquid. As you will see it outside, it doesn't, the state of the liquid doesn't change, and it's the circulation of the liquid, which in our case is done through a cooling distribution unit which contains pumps, so it's forcibly circulating the liquid. It's that circulation that takes away the heat, together with the secondary loop that can be water, for example, and the water can be reused, as we were seeing this morning, to heat part of the building, or it can be just freely evaporated to the outside. It depends on the type of facility. So this is a picture of what it looks like. This is the previous version of the unit that you see outside. It's slightly taller, it was slightly narrower. I will show you the various differences. just to give you an idea. We usually recommend people to operate in this type of environment with gloves, but it's not because the liquid is toxic. Actually, our liquid is food rated and it's biodegradable, so it's perfectly safe to touch and to handle. We recommend the gloves because it's slippery. It's kind of viscous, and it's the viscosity that it enables the fluid to take efficiently the heat away, but it can be slippery whenever you are manipulating something, so it's recommended to do it with gloves. And these are the advantages that we can provide with this type of solution. So let's go a little bit in detail of each of these advantages. So how do we provide reduced energy consumption? So the first thing, and the most simple one, is that we take out all of the fans from the hardware. So there are no moving parts inside the liquid. You can submerge the switches as well. You can submerge every type of hardware that you want. It's completely, we just need to take the fans out. For some hardware manufacturers which collaborate with us very closely, they provide us with versions of the BIOS which already support operating without fans. For others, we have our own chip, our own PCB that just provides a fan emulator, so it just sends a pulse to the hardware and the BIOS doesn't freak out. But the majority of the cost saving are obtained through the fact that we don't need air conditioning anymore. So we can eliminate in total, if you consider the whole solution, we can consume as much as 50% less than a normal air-cooled solution just because we don't have the cost of the crack units. We also increase the computing density by the fact that we can cram much more hardware in the same footprint. This is, if we assume that these are 10 kilowatts rack on average, and we have 200 racks air-cooled in an area of 1,000 square meters, we can, which means we will have a 2 megawatts facility in terms of computational power. We can actually do the same, we have the hardware, we can fit the same amount of hardware in just 20 of our units. These are the big units, not the ones that you've seen outside, but in each of these units we can dissipate as much as 100 kilowatts. Actually, 100 kilowatts is the figure that we give to people whenever the inlet temperature for the secondary cooling is at 32 C. So the water is circulating input at 32 C, output at 37 C, which means that the liquid can operate anywhere between 45 and 60, providing a very uniform environment for these machines. And this, given the fact that you don't have to cool actively the water in, you can have a lot of saving in power on that side as well. But if power is not the thing that you care the most about, whereas density is, you can run the water a little bit colder and you can have much more dissipation. So you can theoretically go way above the 100 kilowatts that we advertise. It's just that we haven't found so far any server on the market that can generate more than 3, let's say, kilowatts in a 2U space. So even with those type of servers, it's very difficult to produce something that goes above the 100 kilowatt figure that we have. We can reduce, of course, also the building costs because we can deploy these things without needing to have very specialized facilities. So, for example, we don't need raised floors. We can deploy a 2 megawatts facility in 3 40-foot containers, for example. Here at the bottom, you can see the 20 containers that we have seen before. And then you have a generator on top, the cooling tower here, and the power for power distribution, of course. So we can deploy this thing, which means it can be deployed in, I don't know, instead of taking 6, 8, 9 months to deploy a new facility built from scratch, you can deploy this thing in a couple of weeks just by delivering the hardware on site. And these things, since they are completely silent, there is no crack again, there are no fans, so completely silent operation. You've probably seen the unit outside, the machines in there are working, they are on. The pump is circulating the liquid, but you don't hear it, which means you can reduce the latency and increase the deployment speed even further. Imagine the small cases. I'm not talking about big facilities like LLNL or the big clusters that are out there, but most of us have worked probably in small centers in which the researchers just needed, I don't know, 30, 40, 50 machines. And this is something you can easily fit in a corner of an office space, and nobody will notice that it's there, but the latency with which they access it will be much lower because it's just across the hall. So there are a lot of benefits, and the benefits are also in the way that we allocate the budget. So as we all know, whenever an HPC center does a procurement round, usually their budget is divided in several factors. And the factor that is actually the most important one is the IT equipment. That should be the factor that everybody cares about. You want the best hardware, or you want the most hardware that you can get. And the fact that you have to spend, these figures are from the Intersect 360, the fact that you have to spend at least 20-something% on your cooling infrastructure means you have less money for your hardware. But if you can reduce the amount that you spend on your cooling infrastructure, you can reuse this money to get either better hardware or more hardware for the same amount of budget, which is very good. So just to recap a little bit, we have these benefits. We have reduction in cooling capex, we have increasing computing density, reduction in capex for building costs, and also increased hardware lifespan, as we mentioned before. And this is what it looks like. You've seen it outside. In this unit, which is 22U, or we also support the Open Compute project hardware, so we support both standard 19 inches servers and 21 inches servers. We can fit either 22 U's or 21 open U's, because the open U's are a little bit thicker or wider, depending on how you look at them. And then we have another form factor which is almost twice the size of this, yeah, we have monitoring of these things. So the CDU, which is the cooling distribution unit that sits there, I'll show you outside, has sensors inside, so you can monitor the temperature, you can monitor the flow of the liquid, and all of this data can be beamed up to our facility, so we can do active monitoring of our solutions that are deployed in the field. We can also mount more than one CDUs. It means we can go fully redundant in order to be tier 3 and 4 compatible. And we can stack these units one on top of each other in case you want to reclaim the vertical space that might be considered as lost since the rack is on its side instead of being vertical as you're normally used to. And thanks to all of these things, we can provide, if we consider an average in the industry, I know that some of the HPC centers are providing better PUE already, but the average in the industry, not just in HPC, but as a whole, is around 189, 17, 16, depending on who you ask. But with this solution, we have a certified PUE of 1.03. And this is including everything, all of the benefits that we have talked about. And of course, since this is an HPC venue, we also employed a lot of HPC research in designing these machines. We have a team of engineers, both experts in chemistry and CFD, which model the way in which the liquid flows around the machines. And they also model the distribution of the various components. And in this way, we can simulate before we get into the production state, and we can ensure an homogeneous environment for these machines to operate. We have measured the delta T between the various layers in the smart coolant by the fact that we forcibly circulate it. It doesn't go above 5C. It's not like other solutions in the market which only use natural convection and they create layers in the liquid, meaning that sometimes the part of the liquid that's below is much colder than the part of the liquid that's above. And this is not an uniform environment for the machine, and sometimes these people even force you to have hardware whose components are mostly concentrated in this area. So the components that are here do not produce much power. This is something we didn't want. That's why we use pumps in our solution. And again, a little bit of an idea of what it looks like. If we're fine on time, I think we should, for the questions, go there and so I can show you the machine directly. You can also touch it. And very important is the fact that we are working with these hardware vendors and more in order to certify their solutions, their hardware in our solution. We want each of these manufacturers to have at least to uphold the warranty of the hardware that you have bought, because we know that the hardware inside the cooling unit that we provide is the most important part of the installation. We don't have any pretense of being the most important part. That's why we're working with these people. So whenever you have some kind of components to RMA or something breaks, they will also uphold the warranty that you have incurred. And we have deployments in the field already. This is just a brief overview. We have deployments all over the place. A good thing about these solutions is that they can be also sealed and be deployed outside of a normal operating environment, so it can be ruggedized, which means it's very useful to deploy these kind of solutions, for example, where the climate is very humid, like Vietnam, or where the climate is very dry and not like in Saudi Arabia or the Middle East. And that was it. Thank you for listening.
So I guess that there are questions.
Hello. How many time it takes? What is the lifetime of this rack?
The rack is basically a piece of metal, so unless you crash into it, there is no way it should.
But I mean the pumps and these things.
The pumps are rated for an operational life of around 2 to 3 years, depending on usage. But the unit that hosts the pumps is also swappable. And whenever we sell one of these cooling units, we also provide an on-site spare, which means you can just take it out, don't have to stop the operational of the hardware and just put the other one in. We also have a craning system in order to help you lift the machines out, which means you don't have to go there and physically take the machines out, especially for the pumping unit, because it's more than 50 kilograms, so it's not something that a normal person can lift easily in that position. And that's it. The liquid itself is rated for more than 10 years of shelf life.
Okay.
So it will last much longer than your hardware.
Okay, thank you very much.
So I believe it's going to be a lot of questions, but
maybe we can.
I think that you want to do a demo
Exactly.
in front of the unit.
If you would like to join me, we can go there where the unit is, so I can show you in the flesh, let's say, and you can.